All right, crew, what up? We're back at it again. Here we go, working on the disk method. So we're going to move into looking at some volumes here, which is a little tricky because it's three-dimensional figures. So it's kind of challenging to draw, and it's hard for me to do in class on the board. So, there might be some difficulties trying to do this online, but that just means I need you to be, very honest with me and help me out when you aren't sure of something, to just let me know, okay? If you need some extra help, all right? Reach out, ask questions, email me, ask during class, whatever you need to do, okay? So here we have ourselves a nice little cylinder. And I'm just going to make reference to this because in the next slide we'll have some cylinders that we'll use to kind of approximate some volumes, or at least show you how they did that. And just want to show you real quick, the volume of a cylinder here, it's the area of the base, which is just a circle. So it's pi r squared times the height. That's how we find the volume of this bad boy right here. All right. So that's pretty wonderful right there. Pretty fun stuff. Okay. So let's go and move into this right here. And I know we're looking at this and like, whoa, this is overwhelming. What the heck are we looking at right here? Well, so here's the deal, you guys. What we're going to be doing is we're going to be looking at sections of graphs. So in this case, we're looking at this section. I'll call this graph, let's call this f of x, okay? And let me erase this actually. So, and we're going to kind of bound sections of graph, and I'm going to just kind of try and resketch it so it doesn't have that yellowish cylinder thing in the middle there. So here's, let's say this is A, and over here is B, let's say. So it goes like this. Okay, so that's kind of that graph of F-ish up there. And so basically, we're taking, and we have this region of F right here, that's that blue shaded region. And what we're going to be doing with that is we're going to be revolving that around various lines. In this case, we're revolving it kind of the way that I've drawn this about the x-axis. So we're going to take this region and revolve it around. So you've got to imagine if you like put a point anywhere along this part at any point. So if I pick any one of those and I revolve it around the x-axis, any of those points would kind of create a circle as it revolves around. Okay, and so the way that I kind of sometimes will draw this is I will try and draw a reflection of this in the line of rotation, and I don't know, then draw some circles, because again, those dots turn into circles as they get revolved. And so it creates a shape looking kind of like this. Now, the shape actually, I didn't draw it very well. You can see that three-dimensional shape is supposed to look like that up there as it gets revolved around, okay? So again, it's kind of hard to visualize and imagine, but if you take this shape right here, that blue shaded region, and ignore this rectangular part right now, ignore that part for right now, okay? And same thing with this, ignore this section, this section of it right here, ignore that part kind of sticking out. So just look at that blue region right up here. If you were to revolve that about the line that it's sitting on, okay, and it would create this three-dimensional figure right here, okay, with kind of a strange volume. It's not a volume that we know a volume formula for, okay? So what people did back in the day to try and come up with the volume for that before calculus was they approximated it, because they had volume formula for a cylinder, which we just showed in the previous step, or a disk, okay? Is why this is called the disk method. They're referring to these little cylinders here. You see there's these little cylinders that they broke this up into. These are called disks, okay? And these disks right here, they were able to find kind of basically, approximate the volume of this guy right here using, a certain amount of disks, okay? It's kind of like when we did area under a curve and we started by using rectangles to approximate the area under a curve. It's very similar to that, okay? So these disks have the area of, as we just said, pi r squared h. Now, in this case, h is this distance here, which we will be referring to as dx. That will be h, okay? And r is the distance from that black line to the edge. So the radius here, you can see kind of increases of these disks as it moves in the direction that I'm moving on here. So as you go further to the left, the radius of these disks is larger and larger. So anyways, if you used more and more disks, the more disks you use, the more accurate your volume would become. And if you use infinitely many disks, you would get your exact volume. So I know that this page is a big mess and it's looking weird. It's like, what is this leading to? But I'm just going to, hopefully this can be useful as we kind of refer back to some things when we look at some examples. So I think we've just got to dive into an example right now, because again, this is a little bit weird. So let's see what we're going to actually be doing here. It says to find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared, y equals 0, and x equals 2 about the x-axis, okay? Now, I am going to graph y equals x squared, okay? And I'll tell you right now, for y equals x squared, I'm only looking at the positive side of this. So I'm only really focused on the positive side, which isn't specified really in what I'm saying here. Y equals 0 is just right along the x-axis right here. Okay, so I'm kind of highlighting over the x-axis right now. Okay, and x equals 2 is just a vertical line. Let's say it's like right here. Okay, x equals 2. All right, there's x equals 2. There's y equals x squared. So my region is the region. It's kind of like a triangular looking region. It's not quite triangular because the x squared graph is curved, but it's that region that's let's see if I can kind of this inside here. You can see my pointer is pointing out right here. This region right in here. Okay, we're going to take that region and we're going to revolve it about the x-axis. It tells us to revolve it about the x-axis. So I'm going to do my best to try and get an idea of what this region looks like. So I'll usually kind of with some dotted lines here, do my best to kind of draw a reflection of my region in the line of rotation. And then what I do is I draw some circular cross sections because, again, a big key is that when I revolve, as I mentioned earlier, it creates circular cross sections. Because, again, if you take a point on that graph, let's say take a point right here on the graph, and I revolve it around that line, it would create a circle as it revolves around the line. Okay? So what we create in this case, it's kind of like, I don't know, maybe kind of like a cone on its side. If we turned it over, it'd be a cone, maybe a Hershey kiss on its side. Again, you got to think this is I'm trying to sketch this in such a way that you can see that it's a three-dimensional figure. And what our goal is to find the volume of this, okay? We're trying to find the volume of this, all right? So there's a few things in this process that are going to make it helpful for you. Whenever we are revolving around a line, okay, it always creates circular cross sections. So my cross sections, and I'll get more into that here in a second, are circles and have the area formula A equals pi r squared. Okay, A equals pi r squared. One of the big keys is coming up with what is r. Okay, so now I'm going to sketch r. Now, you're going to hear me in many, 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 many examples say the same thing over and over again because it's so valuable. Okay, and that is, I think it is so valuable to draw a sketch of your region and to draw your radius. Okay, and I'll go over this more in just a second because you don't have to draw the reflection, and I'll show you what I would expect you to draw on your paper. So to draw, well, let me actually just do it right now. So if I was giving this on a test or quiz, what I would want to see is that you drew out your region, okay, which is the x squared graph, the y equals 0, and x equals 2 right here, okay? And you draw your radius. Now, the way you draw your radius is you start with your pen or pencil on the line of rotation, okay? So, it could be anywhere in that region. So you can see I just put a little pink dot there. And you draw it to the edge of your region, okay? So there's my sample radius. Now, as I go back to the drawing on the left here, my radius is representative of these circles. Now, this radius changes depending on where I'm at, okay? Again, depending on where I draw my radius, it could be either longer or shorter depending on where I draw it, okay? So you can see here that my sample radius on the right is kind of, I drew it somewhere in the middle there. So it's, kind of, it's not the longest it could be, it's not the shortest it could be, okay? And so, but the thing that's important to realize is that this radius changes according to this equation y equals x squared. It always goes up to y equals x squared, okay? So this radius right here, the radius that I've just drawn here in this graph right here is x squared, okay? Because the length of that radius is solely dependent on that graph y equals x squared. For instance, like at x equals 1, if I plugged 1 into x squared, I would get y is 1. So at x equals 1, the length of the radius would be 1. If I went out to x equals 2 at the very end there and plugged 2 in for x and got 4, I would see that the radius would be 4. So this long radius right here, for instance, is 4. This radius in the middle, maybe at x equals 1 is 1. So it changes, but it all changes according to y equals x squared, okay? So the radius is x squared. Now the radius, the trick that I'm going to teach you guys, and I'm going to say this over and over again, the radius is always the top line that it hits. So if I look at my line I drew, I'm looking at the right graph right now. And if I look at that radius, if I look at the top of the radius, what it hits is the graph x squared, okay? And then if I look at the bottom, so go to the bottom, it hits 0. That's the line y equals 0. So it's always the top equation hits minus the bottom, which in this case is just x squared minus 0, which is what x squared is. But that's going to be our trick. It's always the top equation hits minus the bottom. Okay, that's how you find the radius. And I know this is tricky, and we'll see this in many examples over and over again. So hopefully as we get going, it'll be less and less tricky. So what I'm going to do is I'm going to plug in for r, right? I found that r was x squared, so I'm going to plug in x squared for r. And I'm going to simplify that to pi x to the 4th. So what this represents, this is the area of my circular cross section. So you can see, again, my graph has these circular cross sections, okay, that start over here at x equals 0 and continue until I get to x equals 2. And the area of those cross sections is determined by this formula pi x squared. You know, when I'm at 0, obviously that one actually at 0 would be 0, but as I move to the right, the area gets a little bit bigger and bigger, and it keeps getting bigger as I move to x equals 2. So what I do is I integrate this pi x to the 4th. I like to put the pi outside the integral, okay, from 0 to 2, again, because I started at x equals 0, I'm going to x equals 2. You can see how my cross sections are moving from left to right here, of x to the 4th dx, okay? And the reason I showed the whole last couple slides where the volume formula is, you know, pi r squared h, well, here's my pi, here's my r squared, and the dx is like my h, okay? So that's where this kind of comes from, is that pi r squared h right there, okay? All right, now in this case, this is a integral that I can evaluate easily by hand, so I'm going to do that. I'm going to leave the pi outside, and I'll just put a bracket around my antiderivative. X to the 4th antiderivative would be x to the 5th over 5, okay, from 0 to 2. And then I'll just plug 2 in for x. So it's 2 to the 5th, it's 2, 4, 8, 16, 32. So it's going to be 32 over 5 minus, when I plug 0, and it's just 0. And that then simplifies to 32 pi over 5. So that is the volume of that weird Hershey Kiss looking, you know, region that I've graphed over here. Okay, that's the volume. So once again, you do not need to draw this out here where you draw the reflection and the sample cross sections. What I would like to see is you draw out the region, okay, over here. You draw out the radius, like I've seen here, and then you can use that to fill in this formula and then end up integrating that. And again, I know right now it's a little overwhelming and weird, and we'll keep looking at examples. And as you look at a couple examples, maybe you look back at this one again and watch through the video again, and then maybe it makes more sense. And it says here, find the volume of the solid formed by revolving the region bounded by the graphs of f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. So in this case, we're not going to revolve around the x-axis. So let's start by sketching our region. We should be able to do that by hand. Why don't you guys go ahead and just sketch, you know, graph both of those equations on an xy axis, okay, and get an idea what your region is. All right, hopefully you paused and tried that. I'm going to go ahead and sketch it now. So 2 minus x squared, that's a downward facing parabola that shifted up 2 units. So looking something like that. And g of x equals 1 is just a horizontal line right here at y equals 1, like so. So the region that I'm looking at now is this region right in there. Okay, look at that region right in there. And what I want to do is I want to take and I want to revolve that about the line y equals 1. So once again, I am going to show my reflection and everything. You don't need to do this, okay? But just to get an idea of what this looks like, I'm going to show my reflection here. And so I reflected my region in the line of rotation, and I'm going to draw a few circular cross sections here, like so. There's some circular cross sections that I've drawn, okay? So that's what my shape kind of looks like, and I think I have, yeah. And you know, again, I didn't draw it perfectly to scale, so you can see the actual shape looks like that over there, the 3-dimensional figure, okay? But remember, I don't need you to draw the whole reflection thing, okay? What I would like to see when I am, you know, looking at your test is I would like to see this, that you have drawn your region, okay? So you drew 2 minus x squared, you drew y equals 1, okay? And you draw your radius. That's what I want to see, okay? So again, I don't need to see this guy on the left. Don't need to see that. What I want to see is your region, and now I'm going to draw my radius, okay? And my radius, remember, it starts on my line of rotation. So I can start anywhere. My line of rotation, remember, is y equals 1, anywhere within the region. Let's say I start right here, okay? And I'm going to draw to the edge of my region. Now, my region is above here in this case, all right? So I'm going to draw up to the, up to that graph right there. So my radius over on these graphs kind of look like this. I have different length of radius depending on where I draw it, okay? But I want to see this. I want to actually see that on your paper when I look, okay? You draw the region and you draw your radius. And again, to draw your radius, I'll say it one more time. You start with your pen or pencil on the line of rotation and you draw it to the edge of your region, okay? Now, to determine my radius, now this will come in handy, the trick that I've been saying on the previous ones. It's the top equation hits minus the bottom. So if I go to my radius and I go up to the top of it, which is right here, at the top, it hits the graph 2 minus x squared. And then I go to the bottom, okay, so I go to my radius again, I go to the bottom, and on the bottom, it hits y equals 1, okay, which is 1 right there. So my radius here, okay, is going to be, I'll just do it outside of the circle here. My radius is going to be 2 minus x squared minus 1, okay, which I'll just simplify to 1 minus x squared. Okay, so that's my radius, which hopefully is sensible, because if I go back to this graph over here, the distance all the way, let me do a different color, let's say do, I don't know, something like this. The distance all the way from the x-axis up to the top here would be 2 minus x squared. When I say to the top, it just is to any point on the 2 minus x squared graph. And the distance here from the x-axis to this point is always just 1. So if I want to find, my goal is to find, this distance right in here. So I'm doing 2 minus x squared minus 1 to subtract that out. Okay, so I don't know how helpful that part was. It's kind of hard to see on that graph that I just drew. But again, the key is, if you look at what I've drawn here, I drew my region, I drew my radius, and to find the length of the radius, it's always the top equation it hits minus the bottom. On top, it hit 2 minus x squared. On bottom, it hit 1. So I've simplified my radius over here, and I use my circular cross sections, right? So it's a equals pi r squared, okay? So for r, I'm going to put in 1 minus x squared. I just found that. So I now integrate that. Remember, I integrate my circular cross sections, because my integral is kind of like, it's like my 3D printer, right? Is printing these circular cross sections starting at this x value, which we'll find in a second, and moving over to this x value here. And so that's my integral is going to add up all those little printed little discs that it's printing out. So it's pi times the integral of 1 minus x squared squared. Okay, now the last thing I need is find my limits here. Shoot, what just happened there? Sorry, I don't know if you saw that, but I had a weird thing pop up on my screen. Okay, so the last thing I need is my limits. So my limit, I can see that it starts from here and goes to here. So I got to think, how can I find that? Well, really, you guys, it's just a matter of finding the intersections between those two graphs, which I could do in this case by hand, okay? If I want to find the intersections, it's just where the equations are equal. So 2 minus x squared is equal to 1. So I'm going to solve this equation. I'll subtract 2 on both sides, divide by a negative 1 on both sides, getting x squared equals 1. And then when I take the square root of both sides, I get x equals plus or minus 1. So this is negative 1 here, and this is 1 right here, okay? So it goes from negative 1 to 1. And there's my integral. And all I'm going to do is set this up. I'm not actually going to evaluate this right now. You could evaluate that integral using your calculator if you wanted to. You actually could do it by hand, but it's a big pain. You'd have to square it out, and it's a lot of work with fractions. So I'm not going to worry about that. This is the setup of the integral. Again, you clearly could evaluate this if you were to use your calculator, or you could do it by hand and take a long time. Okay, but I'm just going to leave it as setting it up. That was the key. I just wanted to set this up. So a quick recap. If you're coming up with a question like this, sketch your region. Draw your radius, okay? Your radius always starts from the line of rotation and goes to the edge of your region. To find what your radius is, it's the top equation the radius sits minus the bottom. You plug that into your a equals pi r squared equation, because revolving always creates circular cross sections, okay? And then once I plug that in, I end up just integrating. And, in this case, I had to find the limits using an intersection.